So with that, let me try to introduce the second speaker, Youxue Zhang. And so all of you who've been working on diffusion, that Youxue is a name that would be very familiar to. There's relatively little to introduce. Now, just in terms of what he has come through, he did his bachelor's degree in University of Peking, and then moved to the United States, where he did a PhD at Columbia University, working with Dave Walker, I believe, and which was followed by a postdoc at Caltech with Jerry Wasserberg and Ed Stolper, and that's where he did the work that I was just talking about. So he really changed how we think about water diffusion in melts and glasses. So there's a lot of papers on that. And after Caltech, he moved to University of Michigan as a faculty, where he's been ever since. He's been recognized in many different ways. I'll just pull out one particular award. He got the Clark Medal for the Young Scientist Award of the Geochemical Society back in the early 90s. And since then, he has done many, many different things related to diffusion. He's written a book that's used by various people on kinetics in geochemical systems. And today he's going to talk about multi-component and isotope diffusion in molten basalts. Youxue, all yours.
Thank you, Sumit. Good day, wherever you are. My talk will focus on our recent progress on studying multi-component and isotope diffusion in silicated melts. Hannah introduced the topic very well, introduced the topic of diffusion very well, and also introduced several concepts, for example, the Aronnax plot and some other plots. So that's very good for my talk. So diffusion is due to random motion of many particles, which tend to homogenize the system, because if there is high concentration on one side, lower concentration on some other places, the random motion of the particles would, oh, I should actually do this. The random motion of the particles would lead to flux from high concentration side to the low concentration side. Now, cannot move my slides, strange. Oh, okay. Just start with the diffusion theory, a very short, brief introduction of diffusion theory. In the case of binary diffusion, which is typically what we're dealing with, for example, Hannah's talk dealt with the binary diffusion. So you only consider the diffusion of one component. If it's a binary system, then only one component is independent. The other component depends, the concentration of the other component depends on the first component, because the summation of the concentrations of the two components must be 100. So in ternary diffusion, there will be two diffusive fluxes for component 1 and 2, taken component 3 as the dependent component. And if there are n component systems, and then the diffusion, actually this should be Ji. Ji should depends on the concentration gradient of n-1 component. So this is expressed in a matrix form in this way, where C is concentration vector and D is a diffusion matrix. And you can see this kind of a diffusion equation is very complicated. Due to the complexity of multi-component diffusion in natural melts, usually there are at least 5 components. In the past, when we deal with the diffusion in silicated melts, we only treat components that display normal diffusion profiles. And the method of treatment is effective binary diffusion. In minerals, that's also the same, also effective binary diffusion. In only rare cases, multi-component diffusion would be considered. Even though multi-component diffusion is difficult, we still have to study multi-component diffusion, because diffusion in natural melts, it's always multi-component diffusion. And we geologists cannot simply shy away from it. So there is a problem we want to understand, we just have to deal with the problem. And also when we study diffusion in melts, it turned out many components show abnormal uphill diffusion. So for example, this diagram is taken from an earlier paper by us, Zhang et al. In 1989. During olivine dissolution in andesite melt, MgO diffusion behaves normal. So this is olivine, this is the melt, and X equals 0, which is the interface is here. So MgO concentration in olivine is high, so dissolution of olivine leads to MgO diffusion into the melt. This is kind of normal diffusion profile. However, many other components show uphill diffusion. For example, calcium, very good example of it, it's calcium. Calcium concentration in olivine is low. When olivine dissolves, you would expect low concentration of calcium at the interface. However, you can see that the calcium concentration at the interface is actually very high. So calcium diffuses from low concentration to high concentration. So that is uphill diffusion. Not only calcium shows uphill diffusion, but also other components too. So whenever uphill diffusion is encountered in studying diffusion in melts, we simply note there's uphill diffusion and then we ignore that. Another manifestation of uphill diffusion is that the variability of effective binary diffusion coefficient is very high. So for example, this diagram shows silicon diffusivity in basalt. And this is this is a natural logarithm scale, Arrhenius plot. So silicon self-diffusion behaves very well in the basalt. And if we are talking about the case when there is only one major concentration gradient of SiO2, then this is from quartz dissolution in silicate melt, then this also behaves fairly well at a given composition. So that's the SiO2 diffusion during quartz dissolution. And then, however, if now we collect silicon effective binary diffusivity in other experiments, for example, in the diffusion couple of SiO2 and the titanium TiO2, and also all of these different diffusion couples, we see that diffusivities can vary in very large magnitude. This is more than a factor of 10 variation in the effective binary diffusivity. So that means the concept of effective binary diffusivity has some limitations in application. Another manifestation of multi-component diffusion is coordinated motion of components. So for example, this is also during quartz dissolution into silicate melt. I think it's basalt. And you can see many of these components, they show similar diffusion profiles. The difference is very small. And in fact, it shows, in this case, potassium diffuses with a smaller effective binary diffusivity compared to MgO, so shorter diffusion profile of K2O than MgO, which does not make much sense, because if we study their tracer diffusivity, potassium diffuses faster than Mg in the salt. So all of those means that we have to deal with the multi-component diffusion in natural melts. And the final reason that we studied this, the most important reason, is that an outstanding student came along. So I wrote a book of geochemical kinetics in 2008. And in 2011, I was in a conference, and then an undergraduate student named Cheng Huan Guo came to me, and he said he read my book of geochemical kinetics, and he thought diffusion, multi-component diffusion is a very interesting problem. He would like to study that. I was so excited to learn this, because at the time I was also thinking we should really solve the problems of multi-component diffusion. So then I recruited him to the University of Michigan, and we boldly carried out the project. In terms of to use the multi-component diffusion treatment, so starting from this diffusion equation in matrix form, then the theory actually is fairly simple. We diagonalize the diffusion coefficient matrix, and this is by the eigenvector matrix. This is eigenvalue matrix, diagonal matrix made of eigenvalues, and this is the inverse of the eigenvector matrix. Once we have this, we can go through this. You put this in the equation. We define a W parameter, which is related to concentration. Its concentration multiplied the inverse of eigenvector matrix, and then the diffusion equation becomes diagonalized. So every Wi depends on only one diffusion coefficient, which is the eigenvalue, and so therefore this equation can be solved. And diffusion during minor dissolution can also be solved in a similar way. So therefore, we carried out the work. And so just to summarize our work and the progress in one slide before I go into more details, we pushed and obtained the diffusion matrix in a 7-component haplobasalt and also 8-component basalt by carrying out at least N-1 experiments. Actually, we made 3 more extra experiments at any given condition. And then we solved the multi-component diffusion problem for mineral dissolution. And we also wrote feeding programs and also figured out how to combine diffusion couple experiments and the mineral dissolution experiments to obtain diffusivity. This is done in our 2018 work. So remember that in haplobasalt, there are 7 components. That means it's N-1 minus times N-1, which is 6 times 6, 36 unknowns to feed. In a basalt, there are 49 unknown feeding parameters. So it's tremendous work of feeding. And then we also figured out how to estimate errors on eigenvalues and eigenvectors, which I'm going to talk about a little bit later. And then we defined the concept of nearly degenerate eigenvalues. And then what we found is that eigenvectors do not vary much. This is in agreement with what Chakrabarty et al. Obtained in 1995. And also we made effort to estimate temperature dependence of the D matrix in the basaltic melt. That means we can roughly predict multi-component diffusion in basalt. And we are also investigating isotope diffusion in the multi-component system. So the experimental design is very important, and that's a paper by Trial and Spera. And for N-component system, there has to be more than N-1 experiments. And these N-1 experiments must be linearly independent. Orthogonal would be the best in terms of compositional space. And so this, for example, this diagram shows one design in a ternary system. So if in a ternary system, we can do 3 experiments, and in one experiment, SiO2 concentration would be constant. So there is only CaO, aluminum, and Al2O3 gradient. And in another component, in another experiment, Al2O3 concentration will be constant. In another experiment, then CaO concentration will be constant. So that is the kind of consideration in experimental design. So in our design, we made N-1 experiments in which there is SiO2 concentration gradient, and also the other compensating is either one of those components. And then we also made extra diffusion couple experiments. So the composition we have used, that's a 7-component system in a haplobasalt. That's a haplobasalt. That's the composition. The base composition we use, and every time we would change SiO2 by plus or minus 1.5. Then another component, for example, Al2O3 by minus and the plus 1.5 weight percent. The same with the basalt. The basalt composition is roughly similar to a mid-ocean ridge basalt more. However, we increased the K2O concentration because we want to resolve the effect of K2O on the diffusion matrix, and also the value, Dij values related to K2O. If the K2O concentration is too low, we would not be able to resolve that. So this is the starting materials, the experiments. So we have a base composition as I have shown earlier, either a haplobasalt or basalt. Then, so starting from the base composition on one sample, we would add 1.5 weight percent SiO2. Another, and also on this sample, we would minus 1.5% FeO. So the total is still 100%. And then that's one side, one half of the diffusion couple. The other half of the diffusion couple is the base composition minus 1.5 weight percent SiO2. So that's just opposite to this. And then plus 1.5 weight percent FeO. So that's how we put the two glasses together. So if for every experiment, we have to synthesize 2 starting glasses, and we put them together and carry out the experiment. 2 types of experiments have been carried out. Mostly they're the diffusion couple experiments. So this diagram shows when the experimental charge after the experiment for the diffusion couple experiment. So this is for X, it's greater than 0 and X smaller than 0, there's the interface. And so that's a diffusion couple experiment. Here it's a mineral dissolution experiment. So we let anoside dissolve into haplobasalt. And here is the interface between haplobasalt and anoside. So these are the diffusion profiles and the fit to the diffusion profiles. And on this diagram, it shows, this diagram shows this left-hand side, there are 7 panels. It shows the concentration profiles of 7 oxides during anoside dissolution in haplobasalt. So you can see that the fit is excellent. Even this bump is fit well. And then for here, this is for the diffusion couple experiment in the basalt, and in which this case, it's SiO2 and FeO diffusion couple. The major concentration gradients are in these 2 components. Or the other components, they're essentially constant initially, and then there is some kind of small uphill diffusion. You can see that will be developed during the experiment. And this is another one, that's MgK diffusion couple. And so you can see MgO and the K2O, and then the other concentration profiles also fit very well. So it's based on the minimum number of experiments, class 3 experiments, extra experiments, then we fit the experimental data and get a diffusivity matrix. And then the feeding program would provide errors on each of Dij. So we have struggled for years on how to obtain errors on eigenvalues and eigenvectors. So first we thought of error propagation. So for example, if you have your variable is z equal to x times y, then sigma of z, it can be expressed this way. And I talked with applied mathematicians and tried to figure out how to carry out error propagation, but nobody could figure out how to do this. And then we also tried to mount a Carnot method. And so this is to allow Dij to vary within its error range based on the normal distribution of the error. However, we often get unreal eigenvalues when we vary the diffusion matrix, each of the Dij. If you get unreal eigenvalues, we cannot solve the diffusion problem. So therefore, we cannot get eigenvalues, real eigenvalues. So therefore, we cannot use this kind of method to find the errors on the eigenvalues and eigenvectors. And after a lot of struggling, finally, we found a solution, which was actually really simple. Initially we thought that we might want to write a paper about this. And then finally, when we get the solution, it's so simple. And we just made a note in our 2020 paper. So the solution is that instead of using diffusivity matrix as unknown fitting parameters, we simply use eigenvalues and eigenvectors as fitting parameters. And then the fitting program would provide the errors on the eigenvalues and eigenvectors. And also, because eigenvectors, there's 49 parameters. Eigenvalues, there are 7 parameters. So they're more than the parameters in the D matrix. So when we actually try to find errors on every unknown, then we found that the solution, the errors would be actually complex, would have imaginary components. So then we figured out, this is either can only constrain 49 parameters, and therefore it can only provide errors for 49 parameters, which means it can provide errors on the eigenvalues and also n-2 components of the of each eigenvector, because each eigenvector has n-1 independent component, but only n-1, n-2. There's one that we cannot constrain. And that also can be understood because eigenvectors must be unitary. So there is correlation between the independent components of the eigenvectors. And so therefore, this is the result. We got a different D matrix. It's a complicated D matrix. So you can see we find eigen values and errors, and we also find errors on the eigenvectors. And these are the independent components, but one of them, we cannot find the errors. And then I'm listing SiO2 here, even though it's treated as dependent components. I'm listing it here because then we can see what this component, what this eigenvector means. For example, this eigenvector is mostly SiAl exchange, or the other components, they are kind of tiny. Now, if we look at this eigenvector, the last eigenvector, it's the exchange of sodium, exchange of sodium with everything else. So only sodium is positive and everything else is negative. So this is how we interpret the eigenvectors. And that's so the previous slide was for capital basalt. This one is for basalt. And then again, we made this, calculated the eigenvectors and made the interpretation of the eigenvectors. So now this is a summary of the eigenvectors. There is a lot of similarity, but we have not exactly confirmed that eigenvectors are independent of temperature, which we would like to confirm. And I'm going to show you why we encounter difficulty. So for example, in the haplobasalt system, first eigenvector, the slowest eigenvector, it's SiO2 So, and Al2O3, and then there's SiO2, TiO2. Pardon? You cannot hear me or something?
Sorry, you're somebody unmuted. Just go ahead, Youxue.
So you can hear me okay?
Yeah, you're fine.
Okay. And the third eigenvector, the third slowest is divalent versus all other components. The fastest eigenvector is sodium versus all others. And these two eigenvectors are all the same in both basalt and haplobasalt. But the other eigenvectors are somewhat can be somewhat variable. So for example, there is SiO2, Al2O3, but this one is SiO2 plus Al2O3 versus all others. So you can see there is some kind of variation. And also fourth, and then these three eigenvectors are also somewhat, can also vary somewhat. And then after long struggle, when we plotted the eigenvalues versus temperature in an Arrhenius plot, we found that, so this is the third eigenvector, first, second, the third eigenvector, which is divalent versus everything else. The largest eigenvector is sodium versus everything else. They are far away separated from other eigenvalues. Eigenvalue 1 and 2, they are kind of similar. Eigenvalues 4, 5, and 6, they are also kind of similar. So we define this to be near degeneracy in eigenvalues. In mathematical degeneracy means two eigenvalues are exactly the same. When two eigenvalues are exactly the same, then the eigenvector space would actually be in a plane. Any two mutually perpendicular vectors would be a set of eigenvectors. So therefore, eigenvectors would not be uniquely defined. And so when we have near degeneracy, it means eigenvectors are still uniquely defined, but they are more difficult to really pin down. You need better data. And in the second case, it's lambda 4, lambda 5, and lambda 6. They are also kind of similar, and that they are also, we call them nearly degenerate. And of course, that's why there are eigenvectors. These eigenvectors can kind of vary somewhat. So that is the main difficulty that we are facing at the moment, which we're trying to overcome in future work. Nonetheless, we made an effort to make a average eigenvector matrix for basalt. And then we found eigenvalues change with the temperature. And that's the Arrhenius equation. So therefore, once we have done this, we assume invariable eigenvectors, then diffusivity at any temperature can be, this T is not temperature, this is the eigenvector matrix. At any temperature can be calculated this way. So it's this lambda, which depends on temperature in here, and also the eigenvector matrix, which is constant. And therefore we can then predict diffusion profiles using minor dissolution. In haplobasalt, this is actually the fitting because we only have this one minor dissolution experiment. But in the natural basalt, these are the predicted profiles. So predicted curves are in red and the data are scattered in here. So you can see the prediction, it works pretty well. And there is in this case, for olivine dissolution in basalt, somehow potassium is not predicted very well. So now we can now examine the effect of multi-component diffusion in natural magma system. We used our diffusion matrix to examine multi-component diffusion in bushveld or for bushveld system, where there is a debate on sulfide ore formation. They debated on how sulfide became such oversaturated to form the sulfide ores. And some argument is that there is mixing, but the mixing does not seem to work. So then in this diagram, we are plotting the concentration profiles during magma mixing. You can see that FeO diffusion shows uphill diffusion, there's maximum and the minimum. It turns out that sulfide solubility, the sulfur solubility in melt depends strongly on FeO concentration. So when FeO concentration is low, then sulfide solubility is reduced by almost 100 ppm. So that's where you can actually have more easily have sulfide saturation and ore formation. So the conclusion of this work is that we have boldly carried out multi-component diffusion study in an 8-component natural basalt system. And that's like a Star Trek saying, to boldly go where no one has gone before. And this really requires some courage to deal with such a complicated problem. And in the process, we solved many difficulties. And we obtained diffusion matrix be in 7-component haplobasalt and 8-component basalt. We can now roughly predict the temperature dependence of diffusion matrix in the basalt. And so we can roughly predict multi-component diffusion effect. There are still difficulties and uncertainties, especially in the eigenvector matrix. And so we are still working on this. And then we're hoping to improve the data better, and then also continue to investigate multi-component diffusion in other systems. So that's the first part of my talk on multi-component diffusion. The next part of my talk is on potassium isotope diffusion. So we want to understand if diffusive isotope fractionation in molten rocks, molten basalts. We wanted to actually examine more elements, the isotopes of more elements, but so far we only investigated potassium isotopes. So isotope diffusion has actually been predicted to be able to cause a major isotope fractionation in 1980. That's by Zhang. And then Richter et al. Were the first to study diffusive isotope fractionation. And they actually measured, they were able to measure calcium isotope diffusion, resolve that. And then many more studies were followed. And it has also been found that in natural systems, you can also detect diffusive isotope fractionation. For example, magnesium isotope fractionation has been detected. And once you can detect isotope fractionation, diffusive isotope fractionation, then you can apply the data as a geospeedometer to try to infer Cooling rate, or you can also try to infer the mechanism of diffusion. And in the case of potassium isotope diffusion, it actually plays a role in radiometric dating. So the basic theory on diffusive isotope fractionation is summarized in here. The heavier isotope, H is heavier isotope, L is lighter isotope, diffusivity of heavier isotope to diffusivity of light isotope. It's related to the mass of a heavy and a light isotope. And if they isotope diffuse freely as individual atoms, then by Graham's law, the diffusivity ratio is related to the inverse of the mass ratios taken square root. And then if they're diffusing as a free molecules containing the isotope, the element, then the relation is similar, but here capital M, it's a mass of the molecule, diffusive molecule for the lighter and the heavier isotopes. And if isotopes diffuse as exchanging clusters, so these are the clusters MH and ML, and then the mass of the exchanging counter diffusion species, the M, then that's how they are correlated. So theory is available. However, in melt, we don't know the diffusion mechanism. We don't know how they are diffusing in what kind of molecules. And so therefore an empirical approach is used, which is the ratio of heavy to light isotope rate diffusivity equals to the inverse ratio raised to the beta power. And the beta is a fractionation parameter to be obtained from experimental studies. So these are the diffusion couple experiments that showed high contrast in potassium concentration. We used those 6 experiments with high contrast in potassium concentration. And then we measured the isotope ratio. So this diagram shows the expected diffusion behavior. If every isotope is diffusing, can be treated, the diffusion of each isotope can be treated as effective binary diffusion, then potassium 41 would be an error function profile, potassium 39 would be error function profile, and the diffusivities would be different, and that is a delta value. And if we do carry out the calculation based on this kind of equation, so the K2O profile would behave like this after diffusion, and then the isotope ratio, 41 to 39 potassium ratio would behave like this. So on the high concentration side, there is a small minimum because potassium diffused to the low concentration side, and the potassium 39 diffuses more rapidly. So therefore, high concentration side, there is enrichment of 41, potassium 41. And in the low concentration side, there is enrichment of 39, which means depletion of potassium 41. So that's why there's negative, and there is a minimum and there's maximum. The maximum is much smaller than the minimum in this case because the concentration on the high concentration side of potassium, that potassium concentration is very high. A little bit, a lot of potassium 39 diffusing away only causes a small maximum in the isotope ratio. So therefore, we have the concentration profiles and we measure the isotope ratio profiles. And then we fitted the equation and we found everything works well. We found, we fit the profiles well. And the only problem is that diffusivity of potassium from concentration gradient, it's almost 2 times larger. It's almost 2 times the diffusivity obtained from the isotope ratio profile. How could that be? So we have been struggling with this for some time. And then first we thought maybe the data quantity was not high enough. So we got higher quantity data. So in 2018, the data quantity was not very high, but in 2020, we really struggled. We pushed very hard. We got a high quantity data. And also we got a potassium concentration data based on SIMS measurement, and that has also high quantity. Still, the difference persisted. Diffusivity for the chemical diffusivity is higher by almost by factor 2. than the isotope diffusivity. So then we also thought this might be a multi-component diffusion effect. So we used the formulation of Watkins 2014 to figure out how different isotope diffusivity should be compared to the chemical diffusivity. And eventually we got an equation, and then it seems if the cross-term effect between the isotopic cross-term effect it's negative, it's small, then the difference should be small. And we are not really expecting large cross-isotope diffusion. So because when isotopes mix, they mix in an ideal way. So therefore, we're also ruling this out. So therefore, we're still looking for a solution. Then we just look at, you just stare at the feeding curve. And when you stare at the feeding curve, you actually see the feeding, it's not perfect. There's a little bit of misfit here and a little bit of misfit here. And so on the low concentration side, the data actually is more steep than constant diffusivity profile. That means the diffusivity is smaller on the low concentration side. On the high concentration side, the data are actually shallower, and also diffusivity should be higher than this constant diffusivity. And so to further examine the difference, we actually plotted potassium concentration in logarithm scale and overlaid the feeding curve. You can see the low concentration side, the misfit is real and significant. And why would this tiny difference cause large difference in the diffusivity? And that's because when you look at the isotope diffusion profile, the most variation is in this region, which is my distance of -300. At the distance of -300, potassium concentration is really low. So that means isotope diffusion profile mostly depends on K2O diffusivity at a very low concentration. And then, but the chemical diffusivity depends on the average. And therefore, we had to, then we developed the model. We developed a model in which the diffusivity is exponentially dependent on the potassium concentration. And so that is the model, D equals D1 times exponential function of A times concentration of potassium. And therefore we fit the elemental diffusion profile, and then we use this and fit the isotope diffusion profile. And now these D1 values, they are about the same. So they are within error from isotope diffusion profile and chemical diffusion profile. So finally, we resolve this issue of different diffusivities from chemical diffusion profile and isotope diffusion profile. And so now we can examine the beta factor for potassium diffusion. So this is the beta factor as a function of temperature for SI-K diffusion couple. And for the MGK diffusion couple, that's the red colored. So one point seems to be off the trend, but if we ignore this point, then or the data show this kind of positive dependence on temperature. Now, if we compare with the other isotope diffusion of other elements, the beta factor compared with the diffusion of other elements, and this is plotted, the beta factor plotted against the diffusion coefficient ratio. So diffusivity of the element under consideration divided by diffusivity of SI. And you can see that there is a general trend. However, when this ratio, diffusivity ratio, is smaller than 3, the trend is not really, that's not really work well. So that means there is still something we need to figure out. how to understand this part of the data. And so given our result, so because the beta equal to 0.11, we find diffusive potassium isotope variation should be measurable, greater than 1 per mil, much larger than equilibrium potassium isotope fractionation. And we should be able to resolve such variation during magma mixing, crystal growth, and the crystal dissolution. And also, I'm going to go through this rapidly since I don't have much time. And also potassium isotope ratio in lunar basalts varied by only this much. And so because the potassium concentration in the moon is depleted highly, and therefore we found that you cannot use diffusive isotope fractionation to explain the small difference. And this is the conclusion on the isotope diffusion part. And the final, this one point, just want to point this one point, is that the variation of potassium effective binary diffusivity may actually cause extra difficulty in treating K2O diffusion profiles when we were using constant diffusion matrix, which we encountered, which I said the K2O profiles were not fit as well as the other concentration profiles. Thank you very much.
Thank you, Youxue. And yeah, this was a big tour through long multi-component diffusion matrices and isotopes altogether. So yeah, I'm actually glad that these are recorded. So these are things that one can get back to and absorb slowly. And I think it'd be a good learning experience for many people out here.